humanities, and it helps colonies mentally survive. The structure symbolizes all the technical issues to realize both previously mentioned. Me as an executive architect mostly focus on this functional and technical part of the building design. This is, okay, next one. I have decided to establish a long-term goal connected to this technical part to develop the design standards with help of architecture, structure, mechanical, electrical, and plumbing, so-called MEP. Systems should be focused on minimizing the risk of life loss. So the design of a base or colony or even a city on the other planet or moon develop the design standards with help of architecture, structure, mechanical, electrical, and plumbing, so-called MEP. We are now live. Systems should be focused on.
Okay, Shemek, if you can return to the first slide. We had some technical difficulties with our streaming, but I will introduce you again, just so everyone on our live stream knows what's going on. Welcome and thank you all for being so patient, all of you waiting for us for our live stream. We welcome you, and I'm your host, Koen, also known as Next Astro. This stream is brought to you by Nexus Aurora, and we are a global aerospace innovation network. And just a few weeks ago, our team won the Mars Society Mars Colony Design Competition. Today, we have a special talk about evacuation of buildings within one of those Mars colonies by Przemek Matkowski, an architect with 23 years of experience, joining us live from Poland. And before we start, I would like to remind you that we would love to get some of your questions because we have a Q&A as part of this live stream. Leave them below as a comment in the chat, and I will make sure that Przemek can respond to those questions. And with that, I would like to hand it over again, actually, to Przemek. And thanks in advance for the great talk that you're going to give.
Okay. Thank all the audience for patience. Okay. Again, my name is Przemek Matkowski, and today I will talk about analysis of evacuation in Martian conditions with agent-based simulation software on the example of Twardowsky Mars Colony biome. Few words about me. I'm an executive architect having 22 years, as Khan said, professional experience. I design big buildings, like from 60,000 or more square meters, which in fact can be called cities. Briefly saying, I take the idea and make it happen. One of my top priorities in my work is safety. So hereby I want to promote a project in Nexus Aurora architecture, handgate to architecture on Mars. The purpose of this architecture handgate is to establish the real rules and constraints for design on Mars, followed by possible solutions. This guide should help designers think freely of what is possible and to understand what to avoid and how to think of design in completely foreign environment. If you have any thoughts, please submit it to our Nexus Aurora architecture group. We will be waiting for them. So today I will focus on one of the most important things, in my opinion, which is an evacuation of a Mars base. Let's go back to the 1st century before Christ again. And there is a civil and military engineer, architect, Marius Vitruvius Polio. He presented his trees, the Architectura, where he defined a key triad of designing directions. A triad which is to be followed by any architect or a space architect now. So it's function, structure, and aesthetics. Globally speaking, while function is a reflection of people's needs and activities, in other terms, even mission goals, the aesthetics is reflecting all the humanities, which mostly help colonies to mentally survive. And the structure symbolizes all the technicals to realize, to make happen the previously mentioned. So me as an executive architect, I decided to mostly focus on this technical part of the building design. So I have decided to establish a long-term goal connected to this technical part, which is to develop this standards. And with the help of Nexus Aurora, I hope it will be possible, and we make it in a short timeline, where the main accent, my main focus is the people's safety. So safety of the people is a top technical priority in every building or design, in any place, or architecture, structure, mechanical, electrical, and plumbing, so-called MEP systems should be focused on minimizing the risk of life loss. So design a base or colony or even a city on another planet or moon should and must comply with this principle. Therefore, my long-term goal is to define the standards not only for the architecture but also for the structure and MEP systems. This presentation shows a result of current research on evacuation as a part of this main goal. Short-term research on evacuation of the people focused on a few directions. First is occupants' movement speed in terms of reduced gravity, layout of the main building element, major building elements like passages, corridors, staircases, airlocks, safety zones, sometimes called refugee rooms. Simple example show the egress of people. As you may see on the right bottom, early stage base, like 6, 12 people, does not require significant analysis. But when things come to the colonies and cities, such research is a must-be, because in a design process, such analysis must be conducted even on all stages of the design process, as details might influence the evacuation time. And you may see on the right side that 50 people are taking much more time than 6. Okay, so evacuation of the people. To conduct the evacuation simulation, I use a specialized software, Pathfinder, provided by Thunderhead Engineering. This is an agent-based 3D simulation software. Agent is a virtual representation of each occupant. The result of such simulation is an animation showing fleeing agents. The key information for a designer is the time in which all agents completely escape the scene or are located in refugee areas. This is called a successful evacuation. Based on the results, time of a successful evacuation, adjustment and corrections to the building elements must be made. So like number of staircases, width of the corridors, doors, or even the airlock capacity. After changes, the process must be rechecked through numerous simulations and iterations of it, finally lead to the perfect design solution. The result strongly depends on various data the software requires to conduct calculations. Agent profiles, which are physical characteristics of occupants, 3D scene, which is a building we want to test, and a scenario in which describes the main starting layout of occupants and their behavior during the evacuation. So I will now lead you through those points. Okay, so agent profile definition. I will start as they define profile. Agent profile define a size and speed of each single occupant. These are the key parameters that software requires for each agent in order to conduct the simulation. While the size of an agent is identical to Earth, we are all the same people, the movement speed significantly depends on gravitational acceleration. So various scientific groups has conducted locomotion condition research in terms of micro and reduced gravity. My study was based on the results of research published in 2014 by Francesca Silos-Labini, Francesco Laquantini, and Yuri Ivanenko. This material will be available to you after the presentation. I can give you the link. And then So to define movement speed in terms of Martian gravity, the conversion formula must be used. You may see different research. On the left, you may see different researchers' results combined into one diagram. To obtain movement speed on Mars, we need to calculate the square root of Earth speed squared divided by the constant ratio of standard gravitational accelerations of free fall on Mars and on Earth. Down below, you might see the comparison of the movement speeds between Mars and Earth for the male 3039. And yes, this is the same formula for the Moon, but of course the speeds will be lower. But for the simulation to be closer to reality and reflect community, diversity, multiple profiles must be used. Therefore, I created a table with converted values basing on Earth average walking and running speeds. And this table is divided also by gender and age, in which for each profile, its own recalculated data for speed movement. I introduced an impaired mobility as a I also introduced impaired mobility as a reference. Additionally, in the simulation, for the simulation purposes, you will see Earth male 3039, so you can see how fast is in real simulation the agent on Earth, from Earth, moving in the base, in Mars base, if there is a normal Earth gravitational acceleration. So to suit all the software requirements, minimum, maximum, median speeds must be created, and the final data table is to be implemented into the software. For those who are involved in a moon-based project, I have also the same conversion table for Moon. So, but you need to expect lower values. And finally, I want to underline that the time schedule of any activity like construction must be enlarged due to the fact that our motorics in a different conditions, gravitational conditions, are influencing the time we move. Okay. So the next element is a 3D scene. The best 3D scene for complex investigation is the one containing different types of elements, closed and open spaces, zones with high and low activity for tenants, all in one place. Therefore, Twardowsky Colony Base was chosen. It's a second place winner of Mars Society Mars Colony Prize held in 2019. But for the software to work, original design requires some adaptation. Also, new areas have been added. Briefly, Fardowski Base consists of 6 living modules called biomes and the technical production areas. The total number of people is 1,200 occupants, including one biome for hotel. For this particular research, I took one full biome. You can see it on the render view. So you may see the final result of adaptation is ready for testing. It's not that beautiful, but it's functional in terms of the program requirements. Major areas were reflected, so 5 main levels with living rooms and social amenities, food production area, small common space in the bottom level, communication corridors leading to other part of the colony. Okay. So scenarios are chosen to reflect non-standard situations where long reaction time or mass gathering might slow down the evacuation process. Scenario also reflects a starting layout of occupants. Each scenario is tested on assumed evacuation time. For this research, I took 420 seconds, 7 minutes, limit for successful evacuation. But to define a scenario, a few steps are needed. A definition of population of colony to reflect variety of colony occupants layout in the scene. This is a definition of particular starting location in the scene of each occupant. And finally, behavior of each occupant. This designated that his main goals of occupant, like escaping to airlocks, escaping to safety zones, running in panic, but this I excluded from the simulation. So the population of the colony reflects the community diversification. It is important to involve all kinds of people into the simulation. This table shows assumed percentage of population age ranges I have simulated as a sample layout. As a basis, I took 50 by 50 female-male proportion, and around 45% of a mid-age group is provided to provide the most effective workforce during the base lifetime. And taking into consideration that colony is, I took the consideration that colony is up and running for several years, so we can assume some diversification in age groups. The global percentage division you may see can be converted into the real numbers as we base on original Twardowsky design target, which is 1,200 people in a peak time. There is a slight change in population layout for the hotel. You may see it in blue, as I have assumed that also guests will be mostly a mid-range. They will not be youngsters and very old people. Mostly there will be rich people from 40 to 60. Let me underline that this is assumption only, and then no doubt the start of the colony means a presence of very fit people. They will be trained and capable of efficient movement during emergency situations, but this is not the case the building should be ready for. It is better to introduce some less athletic groups to provide margins for inaccuracy of total simulation evacuation time, and further to base architectural, structural, and engineering solutions on such conclusions. For the Nexus Aurora members' convenience, I made a comparison to 2019 OECD data on the population diversity. Please observe the lack of youngsters in my assumptions due to small colony size. But I suggest that in the bigger settlements on Mars, this must be changed towards the world population scheme we have now, which is shown in blue and green, male and female proportions, and in particular range groups. So, scenario and behavior. Taking into consideration previously presented speed conversion table, population percentage layout, we can make a final chart of profiles, and please observe that those colors are not those colors in the future. You will in the next slides you will see them in the evacuation simulation. Each profile is, as you can see, men are blue, women are green, and they are divided by ages. And the older you are, the darker the agent is. And based on all this data is now to finalize the scenario layout in the scene. This one was running away. This was an Earth one. Okay, so. Finally, two variants of occupant starting layout were selected based on major rule that it should reflect non-standard situation. I called them late evening and weekend event scenarios. So late evening assumes tenants mostly located in their rooms, resting after the Martian working day. Some of them are already sleeping. Therefore, the reaction time since public announcement or PR or alarm sound is much longer than normal. Some people are located in common areas like canteen or sports rooms. Everything is calm and nobody suspects the alarm, but the total number of occupants is a biome bed capacity, which is by original design around 200 people, plus some late guests. So like I took like 10%, so it's 220 occupants in one time, but it is late evening. The next one is is opposite. It's a day off. 10% of colonies is on duty to support a normal base operation. But this time, the biome is a community event held in a common space. 3/4 of the colony is present. There are guests from other biomes, and some of the habitants of the biome we are inside are on the levels of the passages, as you were seeing, and next to and some of them are rest and relaxing in the apartments. And the total number of occupants is 855. So it's almost 4 times more than the typical bed capacity of the biome. Okay. Having all scenario assumptions and what was left to do is to spread the occupants in the scene. So based on population assumptions, particular number of tenants for each scenario, they were distributed along the levels basing on their function. So 2 tables were created to show the number of occupants profiles types spread into each biome level. Please note the significant number of people on main common level, it's +4. In weekend event scenario, it's 665 people in this small area. In this area. And then finally, a behavior of each occupant is to be defined. Of course, the main goal of each agent is the successful evacuation. They will try to reach any exit or safety zone. But there are parameters that we need to be defined to provide scenario realizations. They are a little bit technical, but they pardon? I have assumed that panic behavior is excluded, and relaxing, sleeping people react in something like 60 to 90 seconds after public announcement. There are those who are awake or can understand better the situation. They are in common space, react much quicker and 10 to 25 seconds. Finally, those who will not meet the 300 time of successful evacuation will flee into closest safety room. Please note that the total time of evacuation is 420 anyway. But knowing the timing for the work of airlocks and possible crowd forming in exit areas, and it is already understood that these evacuees with egress time above 300 seconds must run into the refugee safety rooms to meet the overall time goal 420. So, a short resume before I will come to the animation and result. I will make a this short resume what we've already learned. So to conduct evacuation simulation, it's required to combine several initial data. It's agent profiles, scenario, 3D scene, and agent profiles significantly depend on movement velocity, and they are varied because of that. Profiles are divided by age groups representing diverse population, which for software means speed ranges. And scenario are chosen to reflect non-standard situation that must be constructed based on population in the colony, occupants layout in the scene, and behavior of each occupant. Okay, I will show now the result animation. For sake of time, it's 4 times faster than normal, and there are some red agents, as I mentioned. They are at speed people to give you the reference. On the left is late evening scenario, 220 people. On the right is most intense, 855 people during the day off and community event. During the animation, please note the time reference given in the bottom right corner of each window. You will see how fast time is moving. So, simulation starts with a public announcement. In both scenarios, there are people in private rooms. On the left, there are almost all the residents. On the right, only a few of them. They are here, they are relaxing, so the reaction for PA is longer. These in common areas react much faster. You may see crowds rushing towards exit and on main level and residential passages. On the left, there are no big crowd forming. On the right, there are some residents seeing crowd jumps already and run towards local safety zones. They quickly fill up and others must run towards staircases. On the left, safety rooms remain empty. On the airlocks provide most smooth flow of the evacuees. On the right, you may see the airlocks work on their full capacity and slowly crowd jams are formed in front of airlock entrances. And occupants are waiting to the next cycle of airlock to work. So people who have to work for airlocks to work start fill up main safety zones located nearby. They might be treated as a compensation pockets. Safety rooms nearby the airlocks require quite significant area to be provided. It may even become a common rule that safety pockets must be provided in places of biggest crowd gathering by airlocks. On the left, even with a long evacuation time, all people flee around 360 seconds. On the right, while safety rooms are almost full, people head again towards airlocks. And finally, all occupants they managed to close last airlock door and evacuate in assumed 420 seconds. It was very close. These animations show, in fact, a highly advanced result of the research, but I do not call it final. I have started with a few safety rooms and small airlock capacity, and through many simulations, I occurred that it was necessary to adapt new zones and enlarge airlocks to get the presented solution. So, this is a small exclusive for Nexus Aurora. I had a chance to see the 3D model and made a first approach and converting into Pathfinder 3D scene. Please note that this is AutoCAD region model, and it is as simple as that. So I started with overall geometry, but still elements are missing, like room definition, functional division or space division, detailed to public and residential areas at least, where people normally conduct their activities. I mean that technical rooms may be presented in a much simpler manner because they do not generate so many occupants. Staircase, communication ramps, passages between rooms and zones also need to be introduced. I make a simple sketch of I do sorry all the designers, original designers. This is my first approach on the staircase layout. Typically there is no lift because they are mostly excluded from the evacuation. They mostly go down to the first level and await emergency teams to use them during the emergency, the rescue process. The missing thing is also a population of the colony, which gives the proportion of each age groups, as I previously mentioned. The scenario's definition and the scenario definition depending on population proportion and functional layout, with extreme conditions like mass gatherings. Sean once mentioned a football field, which means a big public watching, standing around the field and in the passages, watching the game. So my question is mostly how many people will watch it? And finally, I see a big potential in filling up in the middle of the dome. It is if it's going to be a marketplace or with many small streets and a large number of spread of the people be in between, or there will be some office buildings compacting hundreds of peoples in one place. All is up to us. But please remember that any layout, and it has its consequences, and the more divided and complicated layout, or the more labyrinth we create, the slower people orient themselves and find the way out. I decided to answer one of the most common questions I get about the safety zones and their parameters. The safety zone, safety room capacity is now 1.9 square meters per person, as per FEMA recommendation for shelters. It's 220 square feet per person, including all amenities like place to sit densely, common toilet, unisex with dimensions for impaired mobility people, smart storages, spaces like food, water, fire extinguishing means, but no MEP systems rooms included. And they also are I take 10% of the reserve of the minimum evacuees directed to safety rooms. The safety premise is to save at least 24 hours for all the people, best water, oxygen for 48. This is the reaction time for the emergency teams. And safety room layout assumption is that they best located all over the base and every main functional floor or area. Emergency teams must have easy access and escape distance between them should be no longer than 30 meters, as per analogia to Earth, 50 meters, which is kind of a 50-60 meters is a standard to get to the evacuation exit. From the staircase and 60 meters between the safety rooms. Basic features: hermetic environment, hermetic to environment, radiation protection. Doors must provide both mechanical and hand opening and closure. Doors must be equipped with some emergency hatches for access with sleeves or any other external access without opening the whole door. In case of a distant location, more than 10-15 meters from an open space where an emergency team can come with such a sleeve, airlocks, the safety rooms must have airlock, even a small one, because with a very small depth, even 1.5 meters, so they can, so the emergency team can slowly rescue all the people and take them out and drive to the safe other part of the base. All MEP systems must be independent and provide sealed cut off from the main system in time no longer than a permanent closure event. So when you finally close the door, all the systems must shut down, cut off from the main system's support. So, and also no transits of any auxiliary system is allowed via this room. So there will be no leakage possible one. They should be well visible with lead signage with easy access to by any group of people, include even an impaired mobility ones, and especially the older groups. So, for example, no thresholds. It should be sealed tightly from inside the door, and at least one separate toilet with like for impaired mobility size, like with also independent collection system, which might be further connected to the sewage system, but via sealed flaps. Okay, resuming, safety is a top priority issue when designing a base, colony, or a city. Design standards must be established to secure this issue. Nexus Aurora, a hand guide to architecture en masse, is aiming to include design safety measures, and I strongly encourage everyone to contribute to this activity. Evacuation is one of the key elements of those guidelines. Each iteration of crowd simulation leads to design update and changes resulting in final colony layout. With help of specialized software, which should be used on every design stage, it is possible to reduce the risk of life loss. And pedestrian movement, and especially crowd forming in Martian conditions, requires further investigation, as a most of reduced gravity researchers focuses on single human being. And crowd behavior significantly may influence the design of further bases and colonies. And finally, modularity of all major construction elements like staircases, lifts, and corridors is a way to reduce the cost. But final forms must be investigated in many directions, like evacuation, to provide an open space and flexibility of the other parts for further potential changes. And this is only the beginning of the research. Traits like decompression, dynamics of it, smoke forming, visibility protrusion, fire resistance of load-bearing elements still are to be defined. All of this is driven only by one purpose: to write down the standards with a pen and not with a blood. And special thanks to Francesca Silos-Labini, Twardowsky team, Thunder Engineering team, and Mass Society Poland for support. And now I hope for Nexus Aurora to start to blow up. Thank you very much. Now it's the end. Thank you.
Thank you so much for the presentation, Przemek. Very interesting. We have gotten a lot of questions during your talk, which would be great if you could give an answer to all of those. Shall I just start right away? Can you hear me correctly?
Yes, I do, but maybe I can read them. You read them.
Oh, I'm going to read them to you, and you can just answer any way you like. And you could even go to the correct slide if it is helping answering the question. I think one of the questions has already been answered, because one of the questions was about the ideal capacity of these safety rooms. It's 1.9 square meters per person, as you described.
Okay, I already
add something.
Yeah, I have to, because FEMA, it was mostly on FEMA shelters for the tornadoes. I found it because FEMA has some different standards for the different behaviors. So, like for 48 for more than 24 hours, they recommend almost a double space. And the longer you stay, the bigger size you need. And in fact, when you the proportion now, what you have seen in the simulation is like almost 10 to 12% of the whole area of the base is only the safety rooms. It's quite big. It's quite big, and it's very costly.
And I can actually tell you from our experience in Nexus Aurora that we did not honestly calculate that in our designs. As far as I know, we didn't get into that much detail. So it's very interesting that you have joined our team and have put us on a path to more safety, because indeed, as you ended your presentation, we shouldn't be writing this kind of building codes in blood, but in ink or digital ink maybe is the best. So I'm going to go to one of the questions now. Sean Wessels asks, if you could leave airlocks open for 10 minutes before closing them for the first time, would this improve the evacuation rates?
If I could open them earlier, it depends. It depends. Just let me. It depends. It depends. Let me show this one. Just a second. I'll just jump to this one. It depends, because when people are mentally, they are trying to evacuate as far as possible towards. You can see this is at Fardowski Base. In fact, these three rectangles they simulate the rest of the base. So people mostly will try to go towards the airlocks and towards the rest of the base. And if they are seeing already that they will not manage, or the crowd in front of those airlocks here will start to form in a big scale, they will then mostly start filling up the safety zones. In fact, during this my simulation, I make a little bit, it's not a cheating, but I started to fill up those small safety zones at the beginning of the evacuation, rather than to run all the people down, block them in this area near the airlocks, and then let them go back to safety zones. I assume there is a minimum level of training, and people trust the evacuation teams that they will come and save them. If we open them in the beginning, possibly there will be definitely some people, but I doubt that crowd with this logic of I would not say panic, but the need of getting out of the danger, they will start filling up smoothly the rooms and then go to the airlocks. First they run to airlocks, then possibly more smarter and calmer people that will start filling the safety zones. That's why I wanted to provoke such discussions already. I don't know, Sean, I answered your question. I will make such a simulation. It's not a problem. I have a Pathfinder here almost ready to do that.
I think Sean would appreciate that greatly. But since Sean is also on our Discord, maybe you can talk even after this stream has ended. But I'll go to the next question if you're okay with that, because you're now in this software. And there were actually two different people asking questions about that. Jeremy, he was asking if there's a specific software or if you're just manually using 3D software. And Connor McGowan asked through the subreddit Structural Engineering what software you are using as well.
I believe I told that, but as you can see, I'm using a Pathfinder. This is provided by Thunderhead Engineering guys, and they are. This is a specialized software. In fact, this is a software that is based. Its key core is based on algorithms of avoidance of the protrusions. So you get such a you take one agent. You say go to exit, and the agent will program the path all along to get out, but with avoiding all the protrusions. And finally, they made evacuation software out of it. I'll show you something like paths. Paths are interesting. So you will see that each agent, in fact, has already a defined path. It is calculated previously. In fact, for the purpose of the software calculates the path, and the rest is just a 3D visualization for the people to understand. So you can see that those paths are created, and in fact, computer calculates those. How do they behave? I don't know if I've did I answer the question?
I think you did, and it's very clear now, at least to me. If there are any extra questions, we'll see them pop up in the chat. But I'll continue first to some other questions. For example, by IronHex1, he's asking if we could use similar strategies as we do on Earth for increasing speed and grip for Mars. So what kind of specifically designed shoes and floors to make movement faster, for example? Have you thought about that maybe?
Mostly on what cost? Yeah,
it's a good question, but maybe
what cost?
Magnetic shoes maybe.
But this was also my concern during the making a simulation, designing those profiles. I'll try to show them. This is a profile I will see the female 40-49. As you can see, they are speeds. And for example, I excluded bouncing because on Mars it's you have many nice, cool animation that people are bouncing and running very fast. It's not true if you have a crowd conditions, because when you bounce, you just make more injuries and more. You will destroy the whole process. You make it longer even. And with the shoes, possibly. It depends on motorics. If you're in the friction, if you enlarge the friction, possibly you can a little bit speed up, but then you have to have absolutely all the floor with some kind of magnetic or steel, and try to imagine that you have a steel floor in your bedroom. Is it nice? Do you have steel floor in the park? It's not very. It's not a human. It's not very. No, I would not say that it would be very feasible, but of course it can be done like that. There was a very nice question also about during my from another space nut. Thank you for that question again. During my presentation on Mars Society, it was. What about external suits and external escape? I believe it would be even slower, but we can then include bouncing, because outside you are much more spread and you are not limited by the walls, doors, and so everybody just run. But I cannot imagine how it's going to be if you have a Quidditch outside. Game, and then everybody, like 1,000 people, is running towards one airlock, running away from the dust storm. This I cannot imagine now, and the speed of it. Mostly they will be falling, and it won't be very effective. But this is yet to come.
CMAC, I'm not sure if you can hear me. I might. It might be a problem on your end or on mine, but I'm gonna ask you one other question. If you can hear me, that would be great. Can you hear me? Okay, yeah. That's great. I'm gonna try to fix my audio issues, but I'm gonna ask one more question, and that is from Sam. What is the view on these emergency spaces having a secondary purpose when not in use? For example, these community meeting rooms. And I think it's also an interesting question, as you said before, that they will take up a very large portion of the complete colony if we want to do it safely. Could you elaborate on that? Thank you so much.
In fact, any shelter, it's like any shelter on Earth. What do you keep it inside? Mostly you can treat it as a storage, but as soon as you are not providing the the capacity for the people, this room is useless. Mostly that's why they are so expensive, because they should stay empty or equipped only for evacuation. Of course, we can have a little bit more storage. But in fact, this is a common problem with big buildings, big public buildings. I design retail centers, retail malls, and we have lots of corridors inside the building, from the delivery zone to the boutiques and to the other shops. And those corridors mostly serve also as evacuation routes. And this is a very common practice that some tenants and the maintenance people leave things in the corridors. And when the fire inspector comes, he makes a big fines for protruding the evacuation route. And the same is for the refugee rooms. If you put anything inside which is not easily removable and cannot be stored and compacted in this room and leave the room for the people, this room is useless. And that's why it's so expensive, and that's why you need to run simulations to make them the smallest possible size, so they are not costing money. and air and additional systems and so on and so on. And Earth you need to build them finally. Okay. Okay. Yeah. Look, this is a program. This program is focused on on evacuation purposes only. There are other programs simulating the crowd, like mass motion by Oasis. They are simulating the movement of the masses to understand the building, how the building works. But particularly this one is provided only for evacuation. So we have, as I told you, behaviors. So for example, I need to program them. There is nothing coincidental. The only coincidence is the probability layout of randomized. If you have parameters, you can randomize them. So if you can see, I will give you an example. You have minimum and maximum speed, and in between those numbers, you have a standard deviation. Of the probability. There are four or five types in this program of types of calculation, the probability of randomizing in between minimum and maximum. One I used the one which is the one of the slowest, so the most withdrawn speeds. So the parameters are randomized, but it determines I decide. So wherever I am mistaken, this calculation is wrong. But on the other hand, the diversity of it also provides me also a overall look that if I have, let's imagine that we have only females 49. Would it be that is definitely not a case in the Martian base. We'll have to diverse, and from the diversity, more or less, I have the total time of successful evacuation. Of course, you will never simulate the real people because the real people are mostly also behave in a different ways. But in fact, sometimes on the many different already occurred evacuations, that people, for example, only 1% of people are panicking during the evacuation. It's not that like on the movies, on American movies, that you have mother with child screaming and running on the directions. It's not like that. It's mostly people slowly and continuously exit the building. Of course, there are some panic people, but it's very rare, and it does not mostly stop the evacuation. The biggest slowing evacuation factor is the wheelchaired people. They are moving 10 times slower than the normal crowd. So they are like a wall or protrusion that the crowd must flow around, and this is like a slowly moving wall. So getting back to the question, no, people do not behave like those agents do not behave like people. You need to program it, and the more detailed you program, the more real is the result.
I'm going to take over the next couple of questions. It looks like Koen's having some trouble. So I've got a question that I've also want to know. I'm very curious. A lot of these evacuation simulations are based on like a major disaster, like air loss or something. How do you see a fire starting in a habitat? Because when you've got fire, you've got smoke, and it means that top levels are affected first. Also, your evacuation routes are much different because you can cut off evacuation routes and people have to take secondary routes. What's your views on this, and how does this influence evacuation times?
Okay. Yeah, that's true. That's true, Sean. That's what I was talking to space instructor about, presenting another program by Thunderhead Engineering. It is called PyroSim, and this is a software that simulates the development of fire and smoke, because and it exactly locates the let's say here we can locate the fire, and then the software simulates how the smoke rises up and spreads all around and fills down the whole volume. And of course, it depends. It depends on it influences the evacuation routes. So, if I have this model, I can easily make a kind of a protrusion here and simulate the fire. And then the program will recalculate the routes and recalculate the time. But on the other hand, can you say in the building where is going to be a fire? You cannot. It could be everywhere. So that's why many staircases should be introduced. As you can see on the Twardowsky Base, 3 staircases is something very close to minimum. I would say that there should be at least 4 or 5 staircases to provide the proper evacuation time, because distance here is almost 65 or 70 meters. So definitely somewhere here there should be something more. That's why I also introduced the safety rooms. And yes, it will influence, and whatever, yeah, it also should be included in the scenario, to be honest.
So I've got a question. Like a lot of people want to know how to do this, or not just necessarily do this, but to figure out how to get these models for themselves on a hobbyist side. The software that you use is fairly specialized. Is there any way that that people can try and simulate this or get something close to understand this as well as you do from a hobbyist perspective?
I would say no, because Pathfinder and all the crowd simulation programs, they are based on the algorithms of avoiding the protrusions. This is the basics, and there are algorithms. They are all known, and they are available on net. But you need to program them, and then define the pathfinding of each single agent separately in each single second. So you will not do it with 3D Studio, Blender, or Rhinoceros, or even Grasshopper. You will not do it, because this is mostly the program is focused on calculation of the path rather than the visual representation. In fact, those guys might be represented like this. The occupant is as cylinders, and they are still working. In fact, this is the size of the agent, calculation size for avoidance of the any protrusions or walls. So you will never have this intersection between. So no, you will not use it. You will not have any possibility to make such an exact simulation with so many profiles and data without a specialized program. But Pathfinder is not the it's not the only one. There are a few others. At least one in UK, produced by UK, and there's also a big one, Mass Motion, but it is not for evacuation. It's mostly for crowd spreading. But for evacuation, there are 2 in the world. I know and they are two in the world that are popular. Let's say like that. Pathfinder is one of them. One of it.
Another question from one of the, I think it was somebody on Reddit that wanted to know, if you have marshals and people that help out with evacuations, will this improve evacuation times? Because I mean, this is a simulation, and each entity of here kind of knows what they're doing. What do you think having trained people that can assist people to get to evacuation points will do to real evacuation times?
Okay. First of all, one of the key elements is the time of the movement, is the velocity. Velocity of the crowd, of the people. Together they are much slower. This is the first. To improve the evacuation time, all you can do is the same on Earth. Increase number of staircases, increase number of the width of the corridors, in the width of the doors, so there will be no stacking, as you can see just during the animation. So you will see you will not have like that, and just by the doors they are not forming the big crowd jams. So you have bigger doors, bigger corridors, some safety rooms. Possibly if you make a door like 3 meter wide and the passage like 4 meter wide, and they direct people outside, possibly safety zones will not be necessary. But we need to understand that mass of the people will have to be somehow managed. You can manage it via the big doors, big corridors, or via safety rooms and long working airlocks. This is the way how you manage. Then this is resulting on your base, on the form of on number of elements for evacuation, like passages, staircases, and airlocks, and so on. And how to increase it? You can only lower down the time of evacuation like that. The second thing is the work of MEP systems. In fact, mostly during the evacuation calculations, you assume that everything is broken. This is a possibility. This is a possibility that is even in normal life on Earth. It's quite common that the fire is near some electrical boxes that just explode and shut down everything. Even if you have a power generator and you have some backup systems, they also can be broken. Everything what is mechanical, what is not gravitational, what is not natural physics can be broken and should not be included into and considered in the evacuation, because it could break and will not work. So all your plan will fail. But when you have like frost bricks or other bricks and staircases that can resist like 120 minutes, and you have hermetic, manually closed doors, then you are sure that this is pure manual. This is pure physics. They withstand 120 minutes, and the door could be closed manually, independently of any broken system. This is I would not rely on MEP systems, although they mostly serve to lengthen the time of evacuation. But in fact, it should not be taken into consideration significantly, like smoke exhaust, for example. That was the MEP, and this was so you have the physical means to not, let's say, speed up, but to provide the evacuation, and you have mechanical and engineering systems, which should not be taken so much in consideration. And the third one is the training, the boots on all the steel floors, I don't see any other. Maybe then in the future, if you change the motorics of people, so you cut out the legs of everybody and you use the cybernetics. Yeah, that's possible.
That is definitely a possibility. Shemek, can I ask you like a final question, because we already are well underway, well over an hour.
Yeah, sorry.
So no, that's no problem. You're very enthusiastic and have a lot of interesting knowledge to share. So thank you so much for that. But I'm going to ask you a last question, and that's about someone who asked about is everyone going to be wearing a spacesuit because the outside has no or very low pressure, at least on Mars. So how long does it take to put that one on if you are actually expecting people to wear a spacesuit? And wouldn't it be more logical to have many smaller airlocks in parallel rather than stacking up evacuees, which could cause panic and crushing? For example, when maybe one of those evacuation rooms gets filled up. Can you answer that as the final question so we can end after that? Thank you so much.
So I will start from the end. What I have simulated here is the Twardowsky Base with 3 exits. In fact, biome is on the front, and the rest of the base is communicated via those corridors. If we enlarge the number, of course, but you then enlarge the cost. And you enlarge the number of airlocks, you enlarge the cost. This is kind of a balance. And from the suit, I have completely no idea how long you take the suit, but reading the Mars Society competition entry from Nexus Aurora, if we read it carefully, you would notice that there is a suggestion to wear some kind of a 5-minute rescue hood. So it will help you breathing. I don't know about the pressure, but about the breathing, it could be an issue. It could give you this 5 additional minutes. Finally, answering the last part of the question is that every single area should be monitored on the number of people. Everybody who is exceeding designed number of people, like for example, a biome which is provided for 200 people and then 800 people goes inside, and the biome technology and techniques is ready only for 200. The rest must wear or carry some kind of suit or any additional mean of protection in case of pressure drop or the fire, because they will not be able to be safely evacuated using only the small systems. So only part of the base should be provided for the heavy load of the people, and the rest must be controlled and separate, and strictly rules must be defined, which we will write down in a handbook. Defined to lower down the risk that in case of emergency, all the people who should not be there will die. Jesus, again and again, I'm talking about killing.
No, it's a very hostile environment on Mars, so I understand that it is important, all of these safety features. And I think one of the most strong quotes that you use in your talk is that we should be preparing very well, because if not, we will be writing these kinds of building codes in blood, as you say. And it's a bit of a harsh way to say it, but we need to make sure that we make it safe enough before we go there, and not by learning from these kinds of very costly mistakes. In terms of human life, of course. So it's a very important topic. Thank you for sharing so much of your knowledge and nice simulations with us, still now on the screen. Shemek, it was great having you here. It's great that you joined our team with Nexus Aurora. I would also like to invite anyone listening to this who is any type of specialist or is aiming to become a specialist in any of the subjects that are important for making life multi-planetary, which are maybe architects, geologists, even politicians, psychologists, biologists. All of those kinds of people and others are necessary for us to make it possible to live on other planets and in space. Since it is, as we have just learned, a very hostile environment that you really need to think and plan ahead for. I would also like to mention that we have next week another stream by Mr. Bjelkeman. He will be speaking about aquaphonic systems that can be used on Mars and the Moon. So definitely tune in for that at 4 p.m. Next week on Saturday again. Lastly, before we end this stream, I would like to mention that we have a Discord that you can find below this YouTube stream, so you can hang out, take a look at the different projects that we have going on in our global aerospace innovation network, Nexus Aurora, and join one of the teams that specializes in different projects, from architecture to moon bases to planetary vehicles, and even a board game is being developed. So there's a lot of things that you can do or create your own project. And I would also like to mention that anyone else who's interested to do a live stream and share their knowledge and expertise with other people is very welcome to do so in our Nexus Aurora YouTube channel. So make sure that you leave a message down below in this video, or join our Discord server and send a message to Space Instructor, to me, Next Astro, or Sean Wessels, who you all have heard in this live stream. I thank you all for joining us. I thank especially Shemek for giving us such a great presentation, and I wish you all a great day, and see you next week.